will be posted later today. All right. Now, what we did last time, I introduced you to the concept of hypothesis tests, where we have two competing hypotheses, one called the null hypothesis and the other one called the alternative hypothesis. And the whole idea of a hypothesis test is to see if the sample data provides enough evidence to reject the null hypothesis and to accept or support the alternative hypothesis. Right, so we'll do some more examples today, and then I'll give you some more information about hypothesis testing. And then next Monday, we'll have another Zoom meeting. I'll be out of the area at that point, and it'll be at the regular time, and we'll be talking about section 5.1. Today is just completing section or chapter 4, at least the sections that I want you to look at. All right, so let me share screen, and we'll go to textbook. Second here. No. All right. So we're going to go back to section 4.2 just for a little bit. Give me a second. Need to reboot this. Back to 4.2. Now, what we learned last time also is that we need to use some sort of mathematical or number to determine whether we should reject or not reject the null hypothesis, and we came up with this concept called a p-value. And so we'll talk about that in a second. So I'll just do a review, and I'm going to show you StatKey this time, where we're using simulations of the hypothesis test. All right, so we're going to start with this one right here, which is the example I showed last time, where there were some, I guess, some mice that were, some of them were exposed to light while they were sleeping at night, and some were at regular dark conditions. And their hypothesis was that the light would actually be damaging to the mice by increasing their body weight, by increasing their mass. So what's measured here in grams is the mass of each of the mice. You can see in the table here. And there were 10 in the light group and 8 in the dark group. And we averaged their body masses, their body mass gains, I guess this is what this is, not just body mass, but body mass gains. And you can see the light, for just this one sample of 18 mice, the light group had higher weight gain than the dark group. Now, because the light group has, for this one sample, has a greater weight than the dark group, does not mean that the whole population is that way. So the null hypothesis is there's no difference between the two groups. The average for the whole population of body mass gain is the same for both the light group and dark group. But the alternative hypothesis is that, yes, light does adversely affect the mice in that group, and we expect the mean for the population for the light group to be greater than for the dark group. Okay, so what we can do is create in StatKey a distribution of samples, and then take a look at how to come up with a way of measuring how different the sample is from the null hypothesis, that there's no difference in the two groups. So I'll go ahead and go to StatKey. All right, now the type of samples that we create through simulation in StatKey are called randomization sampling distributions. All right, and so we're going to go to difference in means. That's what this is. And pick out that particular one that we're looking at. So let's see, we're for the mice weight gain. Here it is, right down here. Light versus dark at night. That's the one we want. All right, and then here is the original sample. Here are the 10 that are in the light group, and the average of the 10 weight gains is 6.732 grams. And the average in the dark group of the 8 mice there is 4.114. And our null hypothesis is that there's no difference between the two groups. So we're going to subtract the light group minus the dark group. And for the sample, if you subtract these two numbers, the sample difference in the two means is looks like 2.618, right? So that's the difference between those two numbers, two averages. Now, anyway, the alternative hypothesis says that the light group is bigger than the dark group. The mean for the light group is bigger than the mean for the dark group. And that's called a right tail test. And we see a greater than symbol. We're going to look at the right-hand side of the distribution. I'm going to click right tail, and I'm going to generate 1,000 samples. Now, each of these samples was created with the intention that the null hypothesis is true. So the difference in the means in the middle of this distribution should be around 0. Okay. Now, what we see in this particular graph is 1,000 dots, and some of them are black, most of them are black, and some of them are red. And the red X's or dots represent those samples which are bigger than a certain value, in this case, 2.601. But that's not what we're interested in. We're interested actually in looking at the sample difference between, in the original sample, that's a 6.732 minus 4.114. That difference is 2.618. 2.618. So I'm going to actually go down to this number down here and change it to 2.618. In other words, I'm going to type in the actual sample difference in means, right? And what I notice here is this number here, this 0.025. That is what's called the p-value. So the p-value is basically the proportion of these 1,000 samples to have a mean of at least 2.618, right? And that is called the p-value. The p-value is basically the probability or proportion of samples that have a sample statistic at least as much, at least as extreme as the actual sample statistic from the sample that you have. All right. So in this case, there's about 25.025 times 1,000 is about 25 of these red X's. And those represent those cases where the sample mean for those cases are at least as big as the sample mean for the sample that you have. That is, they're at least 2.618. So this is called the p-value, 0.025. Now, the way to interpret the p-value is we would say the following. We would say if the null hypothesis is true, that is, there's no difference in the means between the light group and the dark group. In other words, light does not affect body mass. There's a 2.5% chance, 0.025, 2.5% chance that, given that the null hypothesis is 0, that we could get a sample of 2.618 or greater. And that's a pretty low probability, all right? So basically, we may be inclined at this point to maybe say, all right, since there's only a 2.5% chance of getting this sample that we got, with the understanding that the population null hypothesis has a difference of 0, right? There's only a 2.5% chance of getting these numbers here. Then we might be inclined to say, well, maybe the null hypothesis isn't really true. Maybe the difference between the means of the two populations are actually bigger than 0. Right? That's of course what the alternative hypothesis is. Now, a little bit later today, I'll show you an exact way of determining whether we should reject the null hypothesis or not. Here, we're sort of inclined to reject it, but some people may reject it, some people may not. So we have to give you an exact way of knowing that when we get our p-value, we should know for sure whether we're rejecting the null hypothesis or not rejecting it. All right, any questions about what a p-value is? So p-value is the probability or proportion of samples, possible samples that would produce a result like the sample that we have or something more extreme than that. Okay, it's the probability of that happening. All right, no questions about that. All right, we'll go back now to the textbook and do another example. Share the textbook. Now, the one we just did is called a right tail test. Right tail meaning that in the alternative hypothesis, we have a greater than symbol. It is called a right tail test. Okay. All right. Now, suppose we have another example. Let's find one. Okay. Right, now here's the definition of the p-value, the one that the definition I just talked about. All right. All right. So let's look for another example. It seems like the book is just obsessing with this one example. All right. So let's see if we can find something else. And I think there is one coming up. And here it is. All right, good. So in this case, it says there was a student survey of 250 students randomly selected. And they were asked to write down a random 4-digit number. All right. So they just randomly picked a 4-digit number. We have 250 numbers in this sample, 4 digits. And what we're looking at is the last digit of those 4-digit numbers. We want to see how many of the 4-digit numbers have a 0 as the last digit. Now we would expect if it was just random, because we could have any number from 0 to 9 to be the last digit of a 4-digit number. We would expect, since there's 10 of those numbers, 0 to 9, we'd expect a 10% chance on average that the proportion of 250 numbers would have a 0 as the last digit, be a 10% chance. Be 0, 1, 2, 3, all the way up to 9. There's 10 of those. So that's our null hypothesis. The null hypothesis is that we expect 0.1, 10% of the cases to have a 0 as the last digit. Now, somebody's proposing, as a researcher, that for some reason people don't like putting a 0 as the last digit of a 4-digit number. So somebody's proposing a hypothesis that the proportion is going to be less than 10%, less than 0.1, right? And then they did, and in this particular sample, after they made this proposal, they've noticed only 12 of the 250 numbers ended with a 0. Now, if you divide 12 by 250, do it with your calculator, you should do it. You should notice that that is 0.048. So the sample proportion in this case is 0.048, 4.8%. And that's well below 10%, 4.1. Right? So it seems like the sample is supporting it, but we need to do a hypothesis test to see if a sample could happen with 4.8% if we assume that the population is 10%. In other words, is it due to normal sampling variability that we get a sample like this? Or can we reject the null hypothesis and state that there's enough evidence to support the alternative hypothesis that the proportion of zeros at the end of 4-digit numbers is less than 10%. All right, so that's what we're going to do. So we're actually going to go to StatKey to look at this. The StatKey is being used here as just a way of simulating this, what they're talking about. They're not actually dealing with real cases. So in this case, this last section here is called randomization hypothesis test. This is what we're using to do our simulations. In this case, we have a single proportion that we're looking at. So we're going to choose that. And we're looking for this particular case of random numbers ending in 0. Here's the one right here. And notice you see on the right side for the original sample, there's 12 out of 250 or 0.048, 4.8% of the sample at zeros at the end of as the last digit of the 4-digit numbers. Now, the null hypothesis is that p is equal to 0.1. Notice that it defaults to 0.5 here. It's always there if as a default, so we have to change it. So I'm going to click inside and type in 0.1. And like, okay. All right, so our null hypothesis is p is equal to 0.1. And if you remember, the alternative hypothesis is that p is less than 0.1. Less than means a left tail test. So we're going to click the left tail here. And we're going to generate 1,000 of these samples. All right. All right. Now, one thing that we want to do here is put our actual sample proportion in the bottom here. And we want to count the number of samples that are less than or equal to the actual sample proportion, right? So we're going to type in 0.048. That's our sample proportion. All right. And in this particular case, which is very interesting, there's only one sample out of 1,000 that has a sample in this sampling distribution. It has a sample with a proportion that is less than or equal to 0.048. So the p-value in this case is 0.001. That's 1 out of 1,000. This is extremely low probability of getting a sample of 0.048 when we're assuming that the proportion is 0.1. Okay, so if the null hypothesis is that we expect 10% of the 4-digit numbers that have 0 at the end, and we're actually getting 4.8%. All right, so 10%, 4.8%. The probability of getting 4.8% as a sample, right, due to sampling variability, it's only a 1 out of 1,000 chance that this sample would actually be one of the samples. 1 out of 1,000. So most likely, in this case here, even without knowing the actual procedure of determining whether we should reject or not, in this case, we'd probably be pretty safe in saying the null hypothesis is false because there's only 1 in 1,000 chance of getting this particular sample. So this sample is actually providing evidence that the null hypothesis is false, and the alternative hypothesis that the true proportion is less than 0.1 is probably true. All right, any questions about that? So this is called a left tail test. All right, so far we looked at a right tail test and a left tail test, and it's determined by the alternative hypothesis. A left tail test in this case is there because of the less than symbol in the alternative hypothesis, and the right tail test in the previous example is there because of the greater than symbol in the alternative hypothesis. Next, we're going to do a two-tailed test. So we'll look for an example like that. Scroll down here. The book, of course, goes through all of this, so you should look at it. All right. So what is this here? All right, so this is a study where they looked at the proportion of males versus females. This is a study that was done a long time ago, males versus females, in terms of playing video games. What proportion of US adults, US males versus US females play video games, all right? Now, in this particular case, we just want to see if there's any difference between males and females. We're not interested if males do more or females do more. We're just interested if there's any significant difference between the two groups. And so the null hypothesis is always equal to the male group, male proportion is equal to the female proportion. And the alternative hypothesis says not equal to. Just interested to see if there's any difference. Right? And it says it right here in the question, the difference in between. And actually, if we scroll up, you'll see the actual study mentioned here. This is a Pew Research study. This is from 2015. There was 2,001 US adults that were in the study, 1,000 males, 1,001 females. 501 of the 1,000 males said they play video games, 477 of the 1,001 females. All right. So that shows what and if you look down here, it shows the sample proportion being 50 for the males being 501 divided by 1,000, 0.501. And for the females, 477 divided by 1,001 or 0.77. All right, so the difference between those two proportions is the difference in the two groups, right? All right, so now what we're going to do is go back to StatKey, find this particular one, this particular case. I'm going to go back because that's a case where we're looking at two different proportions, the difference in proportions. So it would be this case here. And we're looking for the video game example, which is the second one. It says play video games by sex. That's the one. Here's the sample data that we just went over. Notice the difference between males and females is 0.024, difference in the proportions. 0.501 minus 0.477 is 0.024. Now, this is what's called a two-tailed test because the alternative hypothesis has a not equal sign in it. So we're not looking at greater than or less than, we're looking at possibly both cases. All right, so I'm going to check here two-tailed because it's a two-tailed test, and we have not equal to in the alternative hypothesis. We'll generate 1,000 samples. Now, because the difference in males and females is 0.024, we want to change the positive one. See, there's a negative number here and a positive number for two different tails. Notice two tails now have red in them. This is a two-tailed test. We'll change the positive one to 0.024. Right? And now, when we look up above, we see 0.5151 here, we see 0.151 here. Now the 0.151 represents the proportion of samples that are greater than, have a difference in proportions greater than 0.024. Okay. And also we see on the left tail, also 0.151, we see the difference in, we're looking at proportions that are less than negative 0.024. Now the p-value in this case has to be the sum of these two numbers, 0.151 and 0.151. The book says just simply multiply 0.151 by 2. Do that, multiply 0.151 by 2, that with your calculator, you get 0.302. So your p-value is the probability of getting a result of 0.024 or more extreme than that from both ends. So it would be negative 0.024 also. So anything that's bigger than or equal to 0.024 in the right end or less than negative 0.024 in the left end. So So with two-tailed tests, this is something you should write down. We always double the probability that we say. So if it says 0.151, we multiply it by 2. And that is our p-value, 0.302. Now, that tells us there's about a 30% chance of getting a sample like this or something more extreme than that. And most likely that indicates just regular normal variation around the null hypothesis that there's no difference between the two portions, right? Males and females, no difference in watching video games. So the fact that we have at least a 30% chance of getting a sample like this means that most likely we do not reject the null hypothesis. There's not enough evidence in this case, and we're just going to keep the null hypothesis as it is. Now, it's very important to understand that when we do not reject the null hypothesis, if the p-value is sufficiently large, then we do not say the null hypothesis is true. We don't say that. We just say there's not enough evidence to reject it. Now, last time I gave you an analogy for what we do when we do a hypothesis test. The analogy has to do with a criminal trial, if you remember last time. So what happens in a criminal trial? Well, the null hypothesis is that the person is not guilty, right? The person is innocent, all right? And the judge always says in a criminal trial, you need to find sufficient evidence beyond a reasonable doubt that the person is guilty, all right? There has to be enough evidence to reject the null hypothesis of innocence and to support the alternative hypothesis that the person committed the crime. So that's what we're doing similarly in a hypothesis test. We're just looking at the null hypothesis and saying, is there enough evidence to reject it? If there's not enough evidence, we do not reject it. But it doesn't mean we accept it. We never write, I accept the null hypothesis. I've seen students do that, and it's incorrect. You must, because it's possible that the null hypothesis can be true in reality in the whole population. It's still true. So even if we don't find enough evidence to reject it in the sample that we have, it is still possible that the null hypothesis is actually true. So we never say or never accept the null hypothesis as true. There's not enough evidence. We just say we don't reject it. All right. So that's the language we're supposed to use. Any questions about that? All right. Let's get back to the textbook. So basically, I've shown you the three examples, the three different examples of hypothesis tests. There is a left tail test, there is a right tail test, and there is a two-tail test. So those are the three types. So and how do we determine which type of test we have? We determine it by the alternative hypothesis. Like in this case here, if the alternative hypothesis is a not equal to sign, then we do a two-tail test. And we always multiply the p-value by the number that we get for the p-value by 2 to get the true p-value. If we have a greater than symbol here, then we use a right tail test. If we have a less than symbol in the alternative hypothesis, we use a left tail test. We'll do plenty of examples. You're going to see plenty of examples in your homework, and you'll get used to the idea of how this works, okay? So even if you're struggling with the concepts of all of this now, you must read the textbook, you must do the homework. That's the only thing I can tell you. If you don't do either one of those things, that's not a good thing in this course. Even though this is supposed to be an elementary introduction to hypothesis testing, meaning it's the most elementary examples possible, it is still a new language and it's still unfamiliar to you. So unless you practice, you cannot expect good results in your tests that come in, all right? I can tell you that, even if the tests are very, very basic. All right, so what I'm going to do now, I think, these are just more examples of the same thing. like we did some of these last time, is I'm going to go into section 4.3. Now, in section 4.3, we're going to learn a specific procedure that we're going to do so that there's absolutely no chance that you could get the wrong conclusion about whether you should reject the null hypothesis or not reject it. It'll be crystal clear. The first thing we have to understand is that when we do reject the null hypothesis, we are saying that the sample results are statistically significant. In other words, there's enough evidence in the sample results to conclude that the null hypothesis is probably not true, and the alternative hypothesis is probably true. All right, so let's just do an example here, another example. Suppose we have this example here with, I think we looked at this last time, where there's maybe a supermarket that buys chicken. Now, they don't, obviously, these supermarkets, they don't raise their own chickens. They buy them from a supplier, farm or something. And the supplier supposed to be checking for impurities in the chickens and so forth. And probably they don't all do that. Well, if you remember this particular case about arsenic, which is poison, arsenic in chicken. You remember in the European Union, in Europe, it's banned to use arsenic in chicken, but in the United States, it's not banned. But they do have a limit to how much arsenic can be put into chicken, at least according to this book. And it basically, arsenic is measured in a chicken by parts per billion of arsenic. And when it gets above 80, it's considered to be dangerous. So this particular company or supermarket chain wants to test a sample of chickens, not all the chickens, but test a sample of the chickens to see, to measure their arsenic level, and then take the average of that for that sample and see if it's significantly greater than 80. Now, there's going to be normal variation if the true population, the true arsenic level is 80 or less. There's going to be some samples where you're going to see greater than 80 and some that'll be less than 80. But what we're looking basically for is cases, a supplier where it's significantly more than 80, and there's a really small chance that the arsenic level will be 80 or below for the population, and for us to actually see a sample with that much arsenic in it, or having chickens with that much arsenic in it. So we have to do a statistical test. And the null hypothesis is that the mean is 80. You have to understand that when we use equal to, we can also mean less than in this case here, all right? Because less than 80 would be okay also. But greater than 80 is not okay, and we want to check to see if the sample has significantly more arsenic, and to the point where we would actually reject this null hypothesis. And if we do reject it, then we're going to tell that particular supplier, we're not doing business with you anymore. You put too much arsenic in your chickens, and we're finding another supplier. All right, so let's go back to StatKey and actually do this. Okay. So, do this particular one. And this is a case where we're just looking at one mean. So it's going to be a test for a single mean. It's just the arsenic level. And we'll look for it here. Arsenic in chicken, and here it is, second one listed. And notice in the sample, there was only 6 chickens in the sample, not many. Notice that the mean is 91 parts per billion. Now that looks significantly bigger than 80, and you may be inclined actually to think immediately this supplier is no good, right? 91 looks much higher than 80. But we still have to do our statistical test. Now, because the null hypothesis has a greater than symbol, the mean is greater than 80, we must use the right tail test. And we're going to create 1,000 of these samples of size 6. And the mean is 91. So we want to go down here and change this number here to 91 and measure the p-value. Now, interestingly enough, given the data here, look at all the red X's here. Actually, out of the 1,000, 124 or 12.4% of all the samples of size 6 have at least 91 parts per billion as the average arsenic level in their chickens. It's a lot, 12.4%. So there's a good chance here that we're not going to reject the null hypothesis. This seems to be fairly substantial probability that we could get a sample of 91 or even higher. So this is a case where the null hypothesis probably won't reject it. Okay, probably. But the question is, how do we know for sure whether we should reject this or not? How do we know without guessing whether we should reject it? It seems like we shouldn't reject the null hypothesis, but how can we know for sure? Well, this is where we're going to learn something new. I'm going to go to back to the textbook. This is where it'll get better for you because there's an actual decision that you can make. Right? So we're going to learn about what's called the significance level of a hypothesis test. This is basically a cutoff level, where if the p-value is less than this cutoff level, we're going to reject the null hypothesis. If it's greater than or equal to this cutoff level, we're not going to reject the null hypothesis. Now, it's going to be stated in the problem itself what this alpha is. All right, so it's not something you have to figure out. It's automatically given to you in any hypothesis test problem as a student. But if you were actually an actual researcher and you wanted to do a research study on this, let's say you were a researcher for the supermarket chain, what you would do is come up with a significance level before you actually do any sort of testing, before. And the industry itself may have a certain standard. For example, alpha is typically a small decimal, small percentage. So alpha could be 0.05, which is 5%. It could be 0.01, which is 1%. It could be 0.10, which is 10%. Those are the typical ones. Alpha 0.05 seems to be used in much of social science research, such as in psychology and sociology. But sometimes in the other sciences, they may pick a smaller alpha or a bigger one. But typically, I don't see anything bigger than 10% for alpha. So suppose suppose the alpha that we have selected as the researcher for the supermarket chain, suppose that we picked 5%, 0.05 as our one second here. All right, here we go. So suppose here we picked 0.05. So let's go back to our hypothesis test, one that we just did. And we have an alpha of 0.05. Let's take a look at the p-value again. The p-value is 0.124. Now, first of all, if somebody can yell out, is 0.124 bigger than or smaller than 0.05?
Bigger.
Bigger, of course it is. Now, here's the rule. If the p-value is smaller than alpha, which is 0.05 in this case, we reject the null hypothesis. If the p-value is greater than or equal to alpha, 0.05, we do not reject the null hypothesis. So what is our decision here? Should we reject the null hypothesis or do not reject it? Again, alpha is 0.05. And you said the p-value of 0.124 is bigger than that. So what is our decision? Do we reject or not reject? Let me say it again. If the p-value, which is this number here, 0.124, if it is less than the alpha, we reject the null hypothesis and we accept or support the alternative hypothesis being true. If the p-value 0.124 is greater than or equal to alpha, which is 0.05, we do not reject the null hypothesis. We say there's not enough evidence to reject it. All right, so in this particular case, if alpha is 0.05, do we reject or not reject?
We don't reject it.
That's right, we don't reject. You see, it's a simple rule. It's very easy. You just have to know it. All right, we're just comparing two numbers. Is one bigger than the other? That's all there is to it. All right, so here we'll go back to the textbook. All right, so here is the general rule. It's actually in your book, and you should write this down in big, bold letters because you need to know this. All right, the significance level for a test of hypothesis is a boundary below which we conclude that a p-value shows some statistically significant evidence against the null hypothesis. When we say something is statistically significant, we're saying reject the null hypothesis. All right, clear? So here's the rule down here. If the p-value is less than alpha, reject H naught. The results are significant. If the p-value is greater than or equal to alpha, do not reject H naught. The results are not significant, which means we do not have enough evidence to reject the null hypothesis. So this is a clear-cut rule that there's no question about it. If we know what alpha is up front, we just need to determine the p-value. And then compare the p-value to alpha, and then we make our decision based on this rule right here. And that's it. So it's very easy once you know the rule. All right. Okay. Now, if you remember the situation we had just a little while ago with the when we're looking at the 4-digit numbers, and remember we determined that the sample proportion was 0.048. It was 12 out of 250, I believe, of the numbers had 0 as the last digit. Well, that was the sample proportion. And we wanted, and when we determined the p-value, when we actually went into stack key and looked up and determined the p-value, we came up with something like 0.018, right? Something like that. Okay. Actually, that's not true. It was 0.001, right? 0.001. That's what the p-value was. Here it is. Forget about this 0.018. That was something else. So we determined there was 1 out of 1,000 of the samples that had a proportion 0.048 or less. Now, in that case, even if we picked alpha as 0.01, would we still reject the null hypothesis? So you can yell out yes or no. So even if we picked alpha to be 0.01, which is 1%, if the p-value is 0.001, would we reject the null hypothesis? Yes or no? Compare the two numbers. Is 0.001 less than or greater than 0.01? That's all you're doing. Is it less than or greater than? 0.001. Is that less than or greater than 0.01?
We would reject.
That's right, because it's less than, isn't it? 0.001 is 1 out of 1,000. 0.01 is 1 out of 100. 0.001 is less than that. It's going to be less than most alphas. So yes, we're going to reject the null hypothesis in this case here. There's absolutely very significant evidence that the population proportion of 4-digit numbers that are out there are going to be less than, are going to have a 0 as the last digit less than 10% of the time. All right, this is very significant. All right. Here's the case. Here was the light and dark group, right? Where we had a p-value of 0.018. All right. Now, I think mine was maybe slightly different than this, but it doesn't matter. What was done in the book with the randomization hypothesis test, they came out with a p-value of 0.018. Now, suppose alpha is 0.01. Do we reject or not reject the null hypothesis? If the p-value is 0.018, and I'm saying alpha is 1%, do we reject or not reject the null hypothesis? Is 0.018 bigger or smaller than 0.01?
It's bigger, so we don't reject it.
That is correct. Now, suppose we had picked a 5% significance level. Do we reject or not reject the null hypothesis? Thank you, Albert, for saying don't reject. Actually, you said don't reject. I don't know what you were referring to, which one here, but yeah, it's don't reject. All right, what if the significance level was 5%? Alpha was 5%. Do we reject or not reject? The same p-value, but suppose alpha is 5%. What's your conclusion?
We would reject.
Yeah. So it is determined by alpha, isn't it? Alpha determines whether you reject or don't reject. If it's 1% in this case, we don't reject. If it's 5%, we do reject. Now, you may think that's kind of silly, right? But you have to understand that this alpha is selected by, it should be at least selected by the researcher before they do any actual research, before they've even acquired a sample. They've determined what their significance level is. Now, certain fields of study, certain type of research has their alpha that they commonly use. As I mentioned, the social sciences typically use 5%. There might be some other sciences that use 1%. There might be some other business or something that uses 10%. But typically, it's something that's common for that particular research area. So a researcher should select their alpha before they do the research, and so that they are legitimately making this comparison. All right. So it's not really that silly, but the decision is based off what alpha really is. All right. So I just wanted to show you that so that you're not confused by it. If alpha is less than, pick the p-value, we're not going to reject it. But if alpha is greater than the p-value, we are going to reject it. Okay. So it's all depends on what alpha is, what we've selected before the research. All right. Now, the video game example here, males and females. All right. Remember, I think I ended up with a p-value of 0.302. That's after multiplying by 2, right? Remember, you have to multiply by 2 in this case because the alternative hypothesis has a not equal sign, which means it's a two-tailed test. Now, suppose the alpha is 10%. Do we reject or not reject? Suppose our level of significance alpha is 10% in this case here. What is our decision? Do we reject or not reject?
We do not reject.
That's right, because the p-value is bigger than alpha. That is correct. Good, good, good. All right, so that is the decision making that we make. Now, hypothesis tests, ultimately, when we actually do one, after you've done chapter 6 and you've come back, and I've come back, and we come back to class in December, the examples I will show you it will require you to go through a 6-step process because there's 6 steps. We've actually done maybe 3 of them so far out of the 6. The first step is to, through symbols, write down the null and alternative hypothesis. We don't write it in English, we write it in symbols. We're going to use mu for means, and we're going to use p for proportions. We always use parameters, the population parameters, put them in there. And then we determined the p-value, that's one of the steps. And then we made our decision, that's the 3rd step. Now we could, of course, make an interpretation also. So for example, the one we just did, this one right here, because let's say alpha is 10%, we would say something like at the 10% significance level, we would say there is not enough evidence to conclude that that the difference in proportions between males and females, that there's a difference in proportions between males and females in terms of playing video games. All right. So we would state our conclusion based off of the context of the problem. In this case, it's about playing video games, and the two groups are males and females. So we would say there's not enough evidence to conclude that there's a difference in proportion between the two groups. All right. So that would be like a fourth step. That what we have not learned, and what we will learn in chapter 6, is the formulas that need to be calculated. There's actual formulas that need to be calculated to come up with the p-value, because we're not going to be using stat key at all when we take test number 3 and when we take our final exam. The stat key is being used basically as a way of teaching you and allowing you to become familiar with what a p-value really is and how to do this, how to compare it to an alpha. That's all that it is, but it's not exactly what's being tested on in your tests. So we're not there yet, but I just wanted to bring that to your attention, that we eventually will be using formulas. All right. Now, this particular section here, let me see if there's anything else that we should go through. This is another example here. This one with leniency and smiles. You can read through it if you like. This is another two-tailed test. Notice again, you have to multiply by 2, get your p-values, because there's a left tail and a right tail. Actually, this is not the stack. That's not the stack key chart for this. But anyway, 0.0, if alpha was 0.05 in this case here, p-value of 0.046 is less than alpha. So we would, in this case, reject the null hypothesis. All right. If alpha is 0.05. Okay, so I'm now going to go to section 4.4. Now, the homework. By the way, I'm going to extend the homework for chapter 3 and chapter 4 homework. It'll all be due by Sunday. All right, so I'm going to do that later tonight. At all that. So those of you who have had trouble and not been able to complete your homework, just make sure you don't do all 3 parts of a problem. Don't repeat the problem 3 times, because once you've repeated a problem 3 times, you cannot open it up anymore. So I mentioned this in class. When you do the homework, if you're struggling with it, just do 2 attempts at a problem and leave the 3rd one until you hear more or ask a question from me, or get me to answer a question. Right? Because even if I extend it, if you've already done all 3 attempts for a problem, you can't do any more. That's the limit. All right. So anyway, section 4 does not have homework. Sections 1, 2, and 3 do. So you'll be doing homework for sections 4.1, 4.2, and 4.3. 4.4, there's no homework, but you are responsible for a couple topics in here. So I do want to bring that to your attention, what they are. And so let me go through these 2 or 3 topics in chapter 4, show you what is not being covered. Can everybody see this? Say yes. Somebody yell out yes. Can you see this okay? Section 4.4?
Yes.
All right.
Yeah.
Good. Okay. And seems like I have a chat. Maybe somebody's saying it through the chat. Yes. Thank you, Bradley. All right. So this chart here summarizes the decision-making process in a statistics test, in a hypothesis test. Now, running along here, on the left side here, you see it says reality. Now, reality is unknown. What does reality mean? It's basically what's going on in the population. So the test is being done because we don't know anything about the population. We're running the test on a sample of the population. And we're trying to come to some conclusion based off the sample. but we don't know reality. In other words, we don't know in reality for the whole population whether the null hypothesis is really true or really false. We don't know that. The only thing that we're doing is looking at the sample that we have, and we're doing a test to see whether we're going to reject the null hypothesis based off the sample or whether we're not going to reject the null hypothesis. So suppose somebody, some one person in the universe knows reality and they know that the null hypothesis is either true or false. Suppose you reject the null hypothesis. Okay, you reject the null hypothesis, but in reality, the null hypothesis is actually false. So if you reject the null hypothesis and it's actually false, you didn't make an error, did you? Because if the null hypothesis is in reality false and we reject it through the statistical test, we have not made an error. We've made the right decision. Now, we don't know that because we don't know reality. But if this one person in the universe knows reality, they will shout out, yes, you made the right decision. You've rejected the null hypothesis correctly if the null hypothesis is false. Also, if you do not reject the null hypothesis through the test, but the null hypothesis is actually true, okay, then that's also, you didn't make any error there either, did you? Because if you don't reject it and it's actually true, you've made the correct decision. However, if you see in the table, there are two errors that can be made. First error is if you do reject the null hypothesis, but the null hypothesis is actually true for the whole population, then you've made what's called a type 1 error. Type 1 error. On the other hand, if you do not reject the null hypothesis, but the null hypothesis is false, then you've made another type of error called the type 2 error. Now, the type 1 error, now if you were looking at taking a test like a COVID test, and suppose the null hypothesis is that you don't have COVID, and the alternative hypothesis is that you do have COVID, then if you take the test and you get a positive result, right? The test is saying that you have COVID, right? So we're rejecting the null hypothesis that you don't have COVID. But if in reality you don't have COVID, in other words, you get a positive reading on the test, but you really don't have COVID, that is called a false positive. False positive, all right? That can happen. So even if you get a positive COVID test, it's possible that you don't have COVID. So what kind of error is that? That's called a type 1 error. You've rejected the null hypothesis that you don't have COVID, but in reality, you don't have COVID. All right? So you've rejected H naught, but H naught is true. That's a type 1 error. So the false positive is a type 1 error. And as you probably guessed, the false negative, that means you get a negative test, but you do have COVID. That would be not rejecting the null hypothesis in the test, right? Saying you're okay. All right, not rejecting it, but in reality, you do have COVID. So that's a false negative. So that's the type 2 errors in medical terms can be called a false negative. Now, here's the link between what we just learned in section 4.3 and what they're talking about here. The probability of getting this so-called type 1 error, where we reject the null hypothesis, when the null hypothesis is true, that is also called the level of significance. That alpha, that's the probability of a type 1 error. So it's not totally a random thing when people pick 0.05 or 0.01 as alpha. It actually is the type 1, the probability of a type 1 error, all right? So it's almost like, it's sort of like the limit of how much of a type 1 error that you were able to tolerate, all right? That's what the alpha is, right? You can tolerate, if you say, I'm going to choose alpha to be 0.05, you're basically saying that if I reject the null hypothesis, I'm okay with a 5% chance that I'm wrong. that the null hypothesis is actually true, right? I'm okay with that. I'm okay with making it a type 1 error of 5%, right? So that's sort of your tolerance of that. Now, so that's alpha. The probability of a type 1 error is alpha. You need to write that down. That's what alpha is, the probability of a type 1 error. Now, how about the type 2 error? Well, in statistics, they call that beta. I don't know if you're familiar with Greek letters, but beta is looks like a B, all right? But it has a long tail to it. The only thing you need to know for this course is what beta is. It's the probability of not rejecting the null hypothesis when it's actually false. So it's the probability of a type 2 error. That's beta. Now, calculating beta is not easy, and it's not part of our course. So the only thing that you need to know is that what a type 2 error is. That is, we do not reject the null hypothesis when it's false. And you need to know that the probability of a type 2 error is called beta. And that's all you need to know. That's it. You don't need to know anything else about beta. Alpha, however, the probability of a type 1 error is given in the problem. So you need to know what it is, and you need to know that it is used as a comparison to our p-value in determining whether we reject or do not reject the null hypothesis. All right? Any questions about that? So the significance level is the probability of making a type 1 error. It says it right here. Significance letter alpha, that's what we talked about in section 4.3. It's the tolerable probability of making a type 1 error, right? Sort of our limit. So we're comfortable in rejecting the null hypothesis if the p-value is less than that alpha. We're okay with rejecting. All right. No questions? All right. Now this section here in 4.4, if you're actually going to read 4.4, problem with multiple testing, that's complicated. I'm not going to cover it. It's not a part of the curriculum anyway. Replicating results, not going to cover it. That's an advanced topic. I won't cover that either. What I will cover is this idea of practical versus statistical significance. Suppose we run a statistical test like this one here. This one here is, for example, deals with somebody taking a online course to help them take the SATs. All right, so this is some sort of online study program, which you pay money for, and then you want to see if you can improve your score. I mean, that's the whole idea of doing that. So what is the null hypothesis here? The null hypothesis says that this particular course has no effect on your actual score, all right? On your score, no effect at all. Sorry about this. And the alternative hypothesis says that the score that you get on the SATs, the mean score, is going to be better than if you don't take the course. All right. Now, let's say you do a sample, people who took the course, people who did not take the course, and you see that for people who took the course and repeated taking the SATs, they got a 42 points, on average, a 42.7 point increase in their score. Suppose for people who did not take the course and repeated the SATs, they got a 38.5 point increase. So how much better did the course on average provide than not taking the course in terms of improving your SAT scores? Only a 4.2 point difference between the two. However, if you run a statistical test on this, you will find that that 4.2 point difference is significant. Maybe at the 5% level, it's significant. All right, statistically significant, which means we're going to reject the null hypothesis and accept the alternative hypothesis. Now, here's the real question to you. You were taking the SATs. If you remember with the SATs, I think you can get from anywhere from 200 to 800, right? Points in any part of the course, part of the test. Do you really think that an increase of 4.2 points is worth it? All right. Now, of course, you could say, oh, well, I'm getting a 42.7 point increase by retaking the test if I take this course. But look, on average, people naturally get a 38.5 point increase without taking that course. Is it worthwhile taking the course? And the only difference is 4.2 points. Well, if it costs maybe $1,000 or so to pay, is it worthwhile getting that additional 4.2 points on your SAT scores? I don't know about you, but probably I wouldn't spend $1,000. I just wouldn't. Even if the p-value says, in this case, the p-value is 0.0038 in this test, even if the p-value says the alternative hypothesis is true, right? I'm getting a statistically significant result by taking this course. But is it practically significant? And the answer is probably no. It's not worth it. So even if this 4.2 points seems to be correct, it may not be worth your time and money to spend taking this course, because you're not getting much of a bang for your buck here, so to speak. Okay, so you get the idea. So because something is statistically significant doesn't mean it is practically significant in practical terms. It may not be worth it. Right, and then the final thing is sample size. This is something we're going to deal with a little bit later, especially towards the end of the course. But in essence, if you increase the sample size in your sample and do a statistical test, typically you've increased your chances of rejecting the null hypothesis. All right, just probability-wise. Because what happens when you increase the sample size? You remember, what happens is the standard error becomes smaller, right? The spread of the sampling distribution becomes smaller. Okay, so notice here in this case here, this is the same sample, or same not same sample, the same sample statistic. Here is a p-hat, a sample proportion of 0.35 in both cases. But in case one, you have a sample size of 100, and case two, you have a sample size of 1,000. Right. So the sample proportion is the same, 0.35, but notice that when you have a smaller sample size, the data is more spread out. The sampling distribution is more spread out, so you can see a bigger p-value. And the sample size is larger. Notice that the sampling distribution is narrower, and notice the p-value now is much smaller, and have a better chance of rejecting the null hypothesis. So remember, the lower the p-value, the better chance you have of rejecting the null hypothesis. So in general, increasing the sample size makes it easier to reject the null hypothesis. This is something, again, I'll talk about a little bit later, but it says it right here. A larger sample size makes it easier to find significant results if you assume the alternative hypothesis. All right, so that is it for today. It's a lot of information to think about, and I can tell you from experience that the best way of studying this is read this, even if it doesn't all make a lot of sense up front. Even after hearing me, after reading it, it'll at least make somewhat of sense, and then do the homework. All right, so I highly recommend that you read this, do the homework, and you'll be in better shape when it's time to take the test, because I will give you plenty of examples, especially when I get back, plenty of examples how to do hypothesis testing using your calculator. We haven't even used a calculator yet in doing any of this. No calculator is being used, right? We didn't use a calculator, we used StatCade. No formulas yet, nothing like that yet. Starting next Monday is when I start introducing some formulas. And then in chapter 6, we'll get all formulas, and we won't even be using StatCade anymore. All right, that's a lot. Any questions? Anybody? As you're still smiling, it's like, woo, but that's over. Any questions? All right. So my recommendation to you is again, read the book, read these sections, and then do the homework. And there's no homework in section 4.4. And I believe there's a section 4.5 here. We're not even dealing with that section at all. So the only homework is 4.1, 4.2, and 4.3 in chapter 4. And then we're going to have homework in chapter 5, 5.1 for hypothesis test. Okay, any questions, comments? If you have any concerns, just stay behind for a few minutes and let me know. But anyway, have a nice weekend. I'm going to be extending all the homework from chapter 3 and chapter 4. So all of it's due on Sunday. All right. So for those of you who've been struggling, as long as you have some attempts left in a problem, you'll be able to continue. All right. Take care. Have a good weekend. We'll see you next time. And I'll turn
Have
the
a good
recording.
one.
Thank you, Professor. Have a great weekend.
You too.
Take care, Professor.
Have a good one, Professor.
You too. All right.
Hi, Professor.
All right. Hi, Tiffany. You have a question, Tiffany?